Hi, in this video I would like to talk to you about proofs where we need to exploit some number properties or some divisibility properties. First of all, we should give some definition. In general, an even number can be written as 2 times n, where n is just an integer. An odd number, oppositely, it can be defined as 2 times n plus 1. Maybe you know this already, but these definitions are going to be useful when we are going to prove some statement. Another thing that it's important is what is a rational number. If you remember, rational numbers, they are those that can be written as a fraction. So they can be written in a form of p divided by q, where p and q, again, they are integer numbers. And in particular, in this case, q must be different from 0. So using this definition, it's possible to solve a number of exercises. For example, we can prove that the sum of two odd numbers is always even. This is a typical proof. It's also called the direct proof. It's always even. How do I prove this statement? Well, I have to imagine that I have two numbers. I will call them A and B. And I will write them, for example, as 2 times P plus 1 and 2Q plus 1. In this case, I know that P and Q, they must belong to the integer group. So I hope you're with me. I am just defining two numbers symbolically as 2p plus 1 and 2q plus 1. I know that they must be odd because they respect this form, 2 times something plus 1. Then the way I'm going to prove the statement is just summing up a and b. So I'm just proceeding in substituting a with 2p plus 1 and then b with 2q plus 1. I'm going to get therefore 2p plus 2q plus 2. And finally, I can even factorize a 2 here. So I will have p plus q plus 1. Why am I factorizing? Well, because to say that the number is even, it means that I can write it as 2 times something, so 2 times n. So if I identify n as p plus q plus 1, and n it's going to be again another integer number, then I have proven now that this number is divisible by 2. And I'm going to write it here, divisible by 2. And therefore, I can write it here. I can use the implication sign, or I can use also the three dots here. It means therefore, a plus b is even. In the same way, if a number is divisible by 4, I will be able to find an expression that it's 4 times something. For example, let's say that I would find 4 times n plus 1 or 2n plus 1. Or if it's divisible by 5, I will have 5 times a certain expression. Or divisible by 9, 9 times a certain expression. If it's even, I can even demonstrate that it's going to be factorizable as 2 times a variable, now in this case I call it n, times another factor. And if it's divisible by an odd number, it's going to be 2n plus 1 times another factor. In this case, we say that the number is composite. And this is just because the number can be divisible by 2n, but also by the other factor, okay? And in this case, by 2 plus 1 and this other factor. Another application of proofs can be found using the binomial coefficient. I want to show you some statement that can be used in order to prove equality. For instance, you remember that the binomial coefficient is a coefficient that looks like this. So we have n and k. It's written in this way, and it corresponds to a fraction which is n factorial divided by k factorial divided by n minus k factorial. If you remember this way of writing, it's going to be extremely easy. N factorial just means, just to remind you, n times n minus 1 times n minus 2 times blah 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 times 2 times 1. Okay? So for instance, we can prove that n plus 1 factorial divided by n minus 1 factorial it's equal to n times n plus 1. This will become a proof where I'm going to use an equivalence between the left-hand side to right-hand side. So I'm going to work out the left-hand side. So I'm going to write actually that n plus 1 factorial can be written as n plus 1 times n minus 1 and so on. But then it becomes useful just to stop in the second step here. Or maybe not. No, actually no. It becomes useful to go on just one step more and have n minus 1. And here to have n minus 1 factorial. So this was the left-hand side, right? And in this way, you can see that n minus 1 factorial, it's both in the numerator and the denominator. And therefore, you see that I'm reaching the right-hand side. Okay, so QED. Okay, so this is one application. The second one that I wanted to show you, it's actually this one. So we're going to prove that n plus 1 factorial plus n factorial divided by n minus 1 factorial, it's equal to n times n plus 2. All right, so the way I'm going to do this, it's exactly the same as before. So I'm going to develop each term here to have some common term that I can cancel out. So the idea is that I have n plus 1 times n minus 1. And then I will have n minus 1 here, it's factorial, right? I have all the terms left. And then I will have n times n minus 1 factorial here, and then divided by n minus 1 factorial in the denominator. So I can see that n minus 1 factorial factorizes, so I can even put it here in front. And then inside the parentheses, I'm going to get n plus 1 times n plus n. And then everything is divided by n minus 1 factorial. So I can see that this element and this element cancel out. And then I will have that the result is just n plus 1 times n plus n. But this means that I have n squared plus n plus n. It means that I have n squared plus 2n. And this means that this is actually factorizing n. N plus 2, which is the right hand side. So I can even write LHS equal S. And that's it.